Okay, great. So let us continue the transient stability analysis, swing equation solution, graphical solution of the swing equation or equal area criteria. When we have a disturbance and we have unbalance between B mechanical and B electrical, the synchronous generator experiences acceleration and deceleration. And the idea here, the stability condition if the acceleration area equal to deceleration area. So we are discussing several examples, and we analyze the stability of the system using this equal area criteria. Examples in terms of different disturbances, stable change in mechanical input or fault, different fault types, different locations of the fault. So we will examine the stability of the system in all these cases. This is the first example. We already covered it. We have a generator connected to infinite bus, and as we mentioned earlier, in one of the limitation of the equal area criteria is that this criteria is applied only for single machine infinite bus. So you have to neglect the interaction among the generators if you are handling multi-machine system. You can consider all the machines, all other machines except the concerned one as an infinite bus. This is the limitation of this. And we did also some assumption here and there, B mechanical is constant and so on. So we already covered this example, and this is the situation. We have here initial operating point, and then we have a stable change in mechanical power. So this is the final steady state operating point. When we increase stable change in mechanical power, so the mechanical power will be greater than electrical power. So we have acceleration, and then the machine will, according or due to the inertia, the machine will continue. So we have here deceleration, and if we have enough deceleration area, the machine will go back and forth until it settles down at point P. So this area represents the existing deceleration area. And if we have this area to compensate the acceleration area, the system will be stable, and this area, the remaining areas, is considered as the stability margin. So you have here stability margin represented by this area. This is the stability margin. This area represents the stability margin. As you can see, we still have enough deceleration area, so the machine can be exposed for bigger value of B mechanical 2 without losing the stability. Of course, if we increase the B mechanical more and more, then we may not have enough deceleration area to compensate the acceleration. So mathematically, we end up with this equation when we have A1, which is the rectangular area B mechanical 2 multiplied by delta S minus delta 0. Delta S is known, delta 0 is known, then B mechanical 1, B mechanical 2 are all known. The only unknown here is delta M. So if we have delta M, if we solve this and we have delta M less than delta maximum, the system will be stable. Otherwise, the system will not be stable. So you calculate A1 and A2, area under the curve, and so on. But this is simply can be done. And mathematically, at the end, you have, we covered all this material before. Yes, we end up with this equation. Delta M B max, which is known, BM2 is known, delta 0, B max, BM2, all these are known, except delta M. So you solve this non-linear, and we have cosine delta M here, non-linear algebraic equation. You can solve it by trial and error, or you can use any iterative technique like Newton-Raphson or Gauss-Seidel. By trial and error, you can have, you can assume delta M, and you calculate, for example, the difference between the left-hand side and the right-hand side. And you can say here, if delta M equal to this, يبقى left-hand side, right-hand side, we need these sides to be the same. So we examine delta M, and we have another delta M, assume another delta M, and so on. So until you have left-hand side equal to right-hand side. Okay. So one of the wise start of delta M, and usually the system operates at the linear part of the sinusoidal. So we can start with delta M. The initial start with delta M can be set as such. So delta M is equal to delta S, 2 delta S minus delta 0. All are known, so we can start the initial guess of delta M at this point. Okay. Okay, example 2. For the above example, find the maximum additional power Bm which can be applied for stability to be maintained. Yani, what is the maximum value of BM2 in the last example? What is the maximum? What is the maximum step that we can have and the system will maintain its stability? So in this case, delta M here, in this example, the ultimate value of delta M to maintain the stability, the ultimate value of delta M equal to delta max. So in that example, example number 2, what we need is BM2. How much BM2, how much step we can go, and we still have enough deceleration area to compensate the acceleration area in this case. So this is the acceleration area becomes, and this is the deceleration area. So what is the maximum value here? So in this case, delta M, we will take all the deceleration area. So delta M equal to delta max, which is 180 minus delta S. So this is the straightforward example. You can have it as such. So in this case, the acceleration area Bm here is unknown, and the delta M here equal to delta max, and delta 1 is known. Delta 1 is unknown also, but you can express delta 1 as a function of Bm. And Bm equal to B max sine delta 1. So you can express delta 1 in terms of Bm. They are correlated with each other. So what you can do, you can get the acceleration area in this case. Bm0 is known, and the delta 0 is known. So you can get A1 as usual, and A2 is the integration from delta 1 to delta max. And delta max equal to 180 minus delta 1. So, or delta S in the last example. Yeah. So you can get express A1, calculating of A1 equal to Bm multiplied by delta 1 minus delta 0. طبعا these are expressed in radian, minus integration from delta 0 to delta 1, the electrical power B max sine delta D delta. And A2 This is A2, integration from delta 1 to delta max B electrical minus B mechanical, this rectangular area, which is B mechanical times delta max minus delta 1, which is expressed also in radial, these angles. So you can, of course, say A1 equal to A2, and you can do, some, manipulation of this. This is cosine delta and B max cosine delta 1 and so on. This sine delta integration cosine, and you have delta max minus delta 1. And at the end, you can easily do it. There is no magic here, yani. So you can end up with this equation. Bm times delta max minus delta 0 equal to B max cosine delta 0 minus cosine delta max. So let me ask you, what is the unknown variable here? In solving this equation, what is known, what is unknown? Can anybody tell us what do we have here and what we don't have as a numerical value? Ahmad Al-Qannas.
Yes, Doctor. We don't have PM, and we have the rest values.
Do you have delta max?
Yeah, we have delta max. We calculate it from 180 minus D1.
Do you have delta 1?
Delta 1? Yeah, delta 1. Delta 1, I think we have it. We can calculate it if I'm not mistaken.
Bm equal to B max sine delta 1. And Bm was not known. Delta 1 also is not known. وبالتالي delta max also is not known. But you can express delta max as a function of Bm. Right?
Yes, you are correct.
You can say delta 1 equal to sine inverse Bm or Bmax. طبعا 180 minus delta 1 equal delta max. Right?
Yes, Doctor.
So delta max is not known, but we have correlation between them. Delta 0 is known, delta max, B max definitely is known, delta 0 is known, and delta max is the same here. So you can, of course, express Bm in terms of delta max or delta max in terms of Bm, and this is the situation here. So Bm equal to B max sine delta max. طبعا if delta 1 أو delta max equal to 180 minus delta 1, يبقى sine delta max equal to sine delta 1. Am I right? If this is angle 180 minus delta 1, يبقى sine delta max equal to sine delta 1. So when you have here B max, or we have here Bm equal to B max sine delta 1 or sine delta max. They are the same. Okay. Okay. So you can substitute, and then you can see this is the situation now at the end. You have delta max. You express the Bm as you mentioned earlier. You can see Bm here equal to B max sine delta max. So you express it here, Bm, and you can combine all these terms together. You end up with this equation. So this is again nonlinear algebraic equation. We have sine delta max, and the unknown here is delta max. So delta max and sine delta max. So again, you can have trial and error approach. Delta max, you assume left hand side, right hand side, and you can substitute. You can initially guess, and then you substitute with different values, and you can end up with the solution. Okay, so this is the solution of this. The nonlinear algebraic equation can be solved by trial and error or by iterative techniques for delta max. Once delta max is obtained, the maximum permissible power is found. Of course, from this equation, if you have delta max, you can get how much the maximum mechanical power, and we maintain the stability. How maximum or what is the maximum step, and the system is still stable. Of course, delta 1 equal to pi minus delta max. Newton-Raphson method can be used also to solve the nonlinear algebraic equations as follows. You know, Newton-Raphson application, you need you start with initial value, and then you calculate the derivative at the initial guess, delta max 0, and then you can get delta equal to delta max 0 minus f prime over f calculated at delta max 0, and so on. And Newton-Raphson method similar to what we applied in load flow studies. For this is the equation. You can combine delta max here in one side, and then you have a constant value in the other side, and then you starting with the initial guess. Of course, delta max, we expected that delta max to be between pi over 2 and pi. You can start any value 130 degrees, or يعني طبعا in radian you can get it, and then you can calculate derivative at the iteration or the initial value. طبعا we start k, the iteration counter. I start with k equal to 0, and then you can, this is the derivative, and you can calculate the correction value, which is c minus f calculated at delta max over the derivative calculated at delta max. So you can correct delta max by adding this delta max for the new iteration, and then you can iterate here, check for conversions. If you find the difference between delta max in two successive iterations less than equal epsilon, which is very small tolerance, then you can stop. Otherwise, you can iterate here. This is simply the Newton-Raphson method. Typically, these solutions or these problems are solved using the trial and error, but of course, you can use also some iterative techniques here. I hope things are clear. Okay. Let us see another example. For one machine infinite bus, a sudden fault occurs at the sending end of the line. Here, this transmission line near to the bus number 1, we have a fault here. Okay, so the fault is cleared without line tripping. Fault is cleared by itself without line tripping. Post fault configuration the same as pre-fault without line tripping. The configuration is the same, pre and post. طبعا during the fault we have solid connection here to the ground, the configuration is different. Find the conditions for stability and the critical clearing time. And this is, as we mentioned, a very important information that is needed for the protection relay settings. We need the relay to operate before or after. What do you think? We need, if you are calculating مثلا the critical clearing time, this is equal to مثلا 300 millisecond. This is the critical clearing time. So what do you think, Abdulaziz, Khalid?
Before the critical clearing time.
Sorry?
Before,
What is?
before.
Before, oh. You need the relay to operate before the critical clearing time. Yes. طيب عماد, do you have another? خلاص, okay. So this is the, yes, you are right. We need, of course, for relay setting, we need to calculate the critical clearing time. And after critical clearing time, if the fault sustained for a longer period than the critical clearing time, the system will be unstable. No matter what you have taken, plus it's over. So okay, so here we have three cases: pre-fault, under fault, and during the fault. Pre-fault, during the fault, and post-fault conditions. As we mentioned here, without line tripping, the post-fault equal to the pre-fault. But let me ask you, during fault, can we derive the swing equation, or in other words, how much B12 during? How much of the power transfer between the generator and the infinite bus during the fault? How much? Abdulaziz?
Zero.
Zero. Yes, you are right. It is zero. If the fault occurs at the bus, then the power transfer is zero. And later we will see if the fault occurs here, but we still have some power transfer. Okay. So during the fault, the power equal to zero. So how to construct now the B delta or curve and the acceleration and deceleration area? How can we construct this for this simple problem? The machine operates here. Plus we will utilize this line as the mechanical power. I don't need to draw another line. So this is the mechanical power, and this is delta zero, and the system operates at this operating point, and everything is fine. Suddenly the fault occurs at this bus. So how this operating point will move? Ramadan Ali?
Yes, Doctor. It will move down to zero and then shift to the right.
Down. Okay. الباور equal to 0 during the fault. So the electrical power will be 0, and it will continue 0 لأنه time is running. It will continue 0. We have here, if this is a B mechanical constant, and now B electrical initially was here, but during the fault B electrical equal to 0. So this will create acceleration to the system. So the angle will increase as time going on until you clear the fault. You have here delta clearing. You clear the fault, assume after few milliseconds where the angle increases due to the acceleration from delta 0 to delta C. When you clear the fault, where would be the electrical power? Where? Will go where? This is pre-fault. Pre-fault, and this is during the fault. And as we mentioned, Ramadan, in the pre-fault,
it will move up to the curve again.
Again, it will go up to the curve. طيب, let me ask you, Ramadan, since you are with us now, what is the final destination? And after this transient and so on, assume that the system will be stable. Where is the final destination?
I think it will go back to the original point or nearby the original point.
We'll go back to the original point. You are right. Ayub Al-Khalifa? Ayub? You
Yes.
have a question? Yes.
I think it will be increased up to the delta maximum and come back then to the delta C.
Delta C?
So I think it will be settled at delta C, right?
لا, where
in
is
the
delta
curve
C?
would intersect with the delta.
يعني
We have
you
delta
want
naught and we have delta C.
Okay. It will settle here. ومين يعني؟ ما هو دي electrical power, فلا it should be on the curve. Point on the curve. But do you think it will settle here? This is not a steady state operating point. لأن البي mechanical is not equal to the B electrical. ما هو steady state operating point معناه إن البي mechanical equal to B electrical. Okay? So it will not settle here. Yes, of course, it will go here back and forth due to the inertia and the acceleration and so on. But finally, since the pre-fault condition equal to the post-fault condition, same power curve, then this is the steady state operating point. And finally, it will settle back at delta 0. Is it clear?
Clear, yes.
If the fault is cleared by tripping a line, if we trip the line due to isolate this fault, these circuit breakers are open, so we isolate this fault by tripping the line. In this case, the system configuration is different in post fault. So in post fault, we have another B delta curve. And if this is the case, when we clear the fault, this will not go up, will come to the post fault here. And finally, the system will settle down here, unless you switch back the transmission line. So where is the acceleration area in this case? This is the acceleration area, where we have B mechanical greater than B electrical. So this is the acceleration area. طيب when we clear the fault, this angle becomes here. This is the B electric. Okay. Do you think the machine will come back directly to this point? Or it will continue increasing for some time due to the inertia? What do you think? Yes, Hussein?
It will continue for some time also, I think.
So it will continue here. And here we have a deceleration. So this is deceleration area. And the B electrical greater than B mechanical. So this is the deceleration area. And if we have enough deceleration area to compensate this, the system will be stable. And this will be delta max, delta M or delta max or whatever, maximum oscillation. So this is D. Of course, the machine will continue, the angle will increase due to the inertia, and then it will come back, and it will not stop here, it will continue back and forth until it will settle down here. And if you draw the curve, this is delta 0, so you'll see the angle will be as such. Okay, where this is delta max. This is delta max vector. Okay, so can we check the condition for stability and calculate the critical clearing time for this? Now we draw already the scenario. Here, this is the operating point, and then we have this is B during the fault. So we have acceleration area, and if the fault is cleared here, it will continue back and forth, and eventually it will come back to this point. So when the fault occurs at the descending end of the line, power equal to 0, power angle curve corresponding horizontal. Okay, power angle shown as follows. Okay, this is the deceleration area. And in this case, if this is the case, we have a good margin for stability. This is the stability margin. And you still have good amount of deceleration area, deceleration or stability margin, let us say, stability margin. This is the stability margin. Okay. طيب. So you can of course calculate the A1 equal to B mechanical delta 1 minus delta 0 times delta 1 minus delta 0, and then A2 equal to the integration from E to F for delta 1 to delta max, B electrical, B max, and delta minus the area of this rectangular, which is B mechanical, times delta max minus delta 1. So this is the case, this is the acceleration, and this is the deceleration area. Both are equal for stability condition, and when you have them, you can write this one as such. So you can end up with this. So what is known, what is unknown in this? The BM, the delta max,
Unknown.
delta 0, the B max, the delta 1 should be known. And of course, when you clear the fault, you can see either you can express this in terms of time or in terms of angle. And you can say we clear the fault at the angle equal to 70 degrees, delta 1 equal to 70 degrees. Or you can say we clear the fault after, for example, 30 milliseconds. So for the swing equation, you can C with 30 milliseconds, if you integrate the swing equation twice, you will have time t squared over 2 for the integration, and then you can substitute with time to get the angle. So you can, by double integration of the swing, you can have the angle corresponding to the critical clearing time here, or the clearing or fault clearing here. So in this case, you have delta max is unknown, and of course you can solve by trial and error. Okay. The critical, now if we need the critical clearing time, if we need critical clearing time, what do you think? Critical clearing time. What is the maximum value of delta max here? Where is the maximum value of delta max? That means when we exhaust all the deceleration area that we have. At this point. Okay? So if delta max equal to this, which is 180 minus delta 0, we exhaust all the deceleration area that we have. And this is the critical clearing time. If the fault sustained for more than this time corresponding to this angle, clearing angle here, then the system will be unstable. So to get the critical clearing time, we take the whole deceleration area that we have, and at this time, this is the critical clearing angle, which is corresponding to critical clearing time. So we can calculate the critical clearing angle, and then we can get it by integration. We can get the critical clearing time by integration of the swing equation. So now delta max is known, which is 180 minus delta 0. What is unknown is delta C, or delta CC, critical clearing angle. So the critical clearing angle delta C is reached when any further increase in delta 1, the clearing angle of the fault, causes the area A2 to become less than A1. So you don't have enough deceleration area in this case. This occurs when delta max is at the intersection of the line. When we have this, of course, you can get the area of this Bm times delta C minus delta 1, which is A1, A2, the integration from delta C to delta max. Now we have A1 equal to A2, and the delta max is known, Bm is known, delta 0 is known, delta max is known, Bmax is known. So you can right away, this is not a linear equation, but you can get it right away. You know, all are given. You have only cosine delta C. You can see, you can write delta C equal to cosine inverse this value, cosine inverse all this quantity. So you can solve for delta C. If you have delta C, you can get the corresponding time by double integration of the swing equation. Solving the delta C gives the critical clearing angle for the machine to remain stable. To calculate the critical clearing time Tc, the swing equation should be solved. For this particular case, when we have B electrical equal to 0, an analytical solution can be obtained as follows. You can, this is the swing equation, B electrical here equal to 0. This is minus BE, which is 0. And you can, Bm is constant, so you can double integrate. You can have it as such, integrate, and then you integrate again. Then you end up with delta equal to t square here and plus delta 0. So you have delta 0, and then you can, of course, you can get it. Delta is known. Now this is delta C, the critical clearing angle, and you can find how much the critical clearing time here. So T becomes the square root of a certain formula here. T critical clearing time equal to square root of this. Is it clear? Any question? Ayub, Rani?
Doctor,
Yes.
in a few previous slides, we considered the deceleration area. We only took a small part, not the whole deceleration area.
Okay.
In the previous slide, the slide before.
Yes, this
Yeah,
one,
exactly this one. So instead of taking AGF, we took only, EDGF. But the whole area is deceleration, not only A2.
Yes, you're right. So what is your question?
My
And
question,
here, Ayub, here, if I ask you, if I say no, the fault is cleared when delta becomes, assume that in the delta 0 equal to 30 degrees. Okay? The fault is cleared if the angle reaches 70 degrees. How much? Delta max. Maximum oscillation. In this case, you can solve. And if this is A1 and A2, you end up with this equation. And what you need, delta 1 is known. I give it here, delta 1. And then you can get delta max. So this is the maximum oscillation, right? So this is the maximum angle that the angle will oscillate here. This is delta max, isn't it?
yes, Doctor.
And when I ask you about the critical clearing time, when we ask about the critical clearing time and the critical clearing angle, معناها انه we are utilizing the whole deceleration area and the critical clearing time. And we exhaust all the deceleration area that we have. Is it clear?
Yes, Doctor.
Yani we can clear the fault. We can clear the fault before the critical clearing angle, and we can ask for delta max. Delta max definitely will be somewhere below this angle, below 180 minus delta 0. Okay, so this is the maximum oscillation here. But if we ask about the critical clearing time or critical clearing angle, معناها ان احنا we are using or utilizing the whole deceleration area. So this is one case. If we ask about the maximum angle fault cleared at a certain angle here or a certain time, then you can get delta max. But when we ask about the critical clearing time, we utilize all the deceleration area that we have. Okay? Is it clear, Ayub, Hussein?
Yes, Doctor, clear. But the small part, in the left, on the left, Doctor. So we didn't consider it into deceleration also, but it is.
This one?
No, in the slide before.
Yes.
The ADE.
ADE.
Yes.
Manual.
This is also deceleration.
Yes, this is also deceleration, but as yani here initially we are working here, right? And then the power becomes 0, and becomes power 0 here, and the angle increases. When we go, we clear the fault here, then this point will go up to the electrical power, right? And
Yes,
then
exactly.
it will move somewhere here due to the inertia.
Yes.
So this is the deceleration area where the deceleration occurs here. Okay, not occurs here. Did you get the point?
Yeah, so we are looking for the deceleration area to suppress the overshoot.
Yes, We have here the acceleration area. So we need to compensate it by this area of deceleration.
Okay, yeah. Yeah, clear.
And this area is not including here. Doesn't play any role, this area. You know, in this period, the machine accelerates. And then when you clear the fault, this is the deceleration part here. Okay? Is it
Yeah,
clear?
okay. Yeah, okay, clear.
Okay. طيب حسين علي, do you have
Yes, Doctor, I have
question?
a question. Could the critical clearing angle be more than 90 degree or pi over 2?
Could be more than 90 degrees. يعني yeah, of course it could be. Yeah, it could be. يعني it depends only also on the fault type and the fault location. يا حسين, يعني sometimes yeah, it could be. يعني if you have, for example, if the machine is very lightly loaded. يعني لو الماشين هنا مثلا ده البي ميكانيك او ده البي ميكانيك. Okay, but this is the deceleration area, and you have very huge deceleration. This is the acceleration area now, right?
Yes.
So you can, of course, you can continue up to this. This is the acceleration area, and then you switch or you clear the fault, and this would be the deceleration area. So, and this could be equal to this. So yes, in some cases, yes, you can have a critical clearing angle is higher than 90. No problem, could be done. But this depends also on not only be mechanical, but also the fault type. If you have a fault like this one, this is the pre-fault, and this is the post-fault. And this is during fault. يعني حتى during fault ممكن يكون single line to ground fault أو fault at the midpoint of the line, midpoint. وبالتالي there are some of the power transferred during the fault. So if this is the operating point here, and it comes here to the during fault, and it will continue, maybe you still have يعني the acceleration area will be less, and you can have more than 90 degrees. يعني under different cases you can have this situation. Okay.
Okay.
طيب, let us stop for prayer 5 minutes, and then we will come back inshallah. Okay.
Okay.
Oh, okay.
Okay. Assalamu alaikum.
عليكم السلام.
طيب, let us continue. This is the critical clearing time can be calculated by integrating the swing equation twice. So we end up with, so when you integrate at the beginning, you integrate from 0 to t, so you have this, and the initial value is delta 0. About all this in radian. Delta is in radian, delta 0 also in radian. So you can get the time in second. So this is the time closed form solution. And here, this is a closed form solution, and our problem is clear and simple. And we have here closed form for TC. You can just substitute and get. طبعا this is not always the case. If we have, طبعا here we integrate, then B electrical equal to 0. If B electrical not equal to 0, and you have here sine delta somewhere here, in this case you cannot integrate as simple as we have here. So for this specific fault, three-phase fault at the bus, and the B electrical equal to 0, we would be able to get a closed form solution for the critical clearing time. And this is not always the case. For different type of faults or different location, it becomes very difficult to get the critical clearing time. You have to solve the solution, the equations numerically, and you can get the fault duration after which the system will be unstable. So this is the critical clearing time. Okay, for one machine infinite bus, again, let us another example. A fault here occurs at the midpoint of the line. So in this case, during the fault, do we have power during the fault? Or equal or not equal 0? Equal or not equal 0? If the fault occurs here, Hussein, Ali?
It's more than 0. There will be, I mean, a little power.
There will be power transfer. Okay. Can you get the B maximum or the power angle equation or B delta curve pre, during, post fault? Can we have pre-fault, during fault, post fault? Can we get a B max in order to draw three sinusoidal waveforms here? And we have power during fault, we have power here. This is a post fault, but it will be different than the pre-fault if the fault is cleared by tripping the line. And then if the fault is cleared by itself, even pre-fault and the post-fault, they are the same. After some time, the fault is cleared by removing the faulted line. Now, if we remove the faulted line, we have different configuration, pre-fault, post-fault. And this is during fault. طيب, do you think إنه البوست fault will be always less than the pre-fault, or it might go up than the pre-fault, post-fault? Ayub, Khalifa?
Always it will be less than pre-fault, except if we do some modification in the line.
يعني you add some capacitors, you add this, or what do you mean?
Or maybe we add a new line in parallel.
Okay. So usually, خلينا نقول, usually you are right. Usually, the post-fault is lower than the pre-fault. And when you trip this line, the transfer impedance will be higher and be equal to EV over X. So you have only one line. So this X increases and the power will be less. Okay, so if the fault occurs here, can we calculate the during fault? Can we have the during fault transfer power or B max during the fault? Yes, we can. As we discussed earlier, we have here an impedance, we have here an impedance. The point is you need to calculate X1 to transfer reactance. If this is the fault here, we have here, we can, disconnect. This is connected to the ground. If this is connected to the ground, we have here an impedance. We have here an impedance. So this impedance with this impedance of the line and with this impedance, these impedances are Y connected. You convert from Y to delta, so you can get the transfer reactance between X1 and between E and V. وبالتالي هي ديت الترانسفير reactance وكان get الباور during the fault. In this case, some amount of power is transmitted to the infinite bus during the fault. معناه ان ال BE is not equal to 0, and the power angle curve is shown as follows. You can have here 3 curves, before fault or pre-fault, and post-fault, and during fault. So the scenario will be as such. Initially, we are working here, and when the fault occurs, this point goes down with the during fault. We have the acceleration, the angle will increase. If you clear the fault here, then this point will go to the post-fault, and the post-fault here is not equal to the pre-fault. And due to this acceleration area, we have B mechanical is greater than B electrical. Then we have this by inertia, it will continue, but it will have a deceleration area here, and it will back and forth. And the final destination, where is the final destination of this system? Where is the steady state operating point after clearing the fault? This is the after fault. Ramadan Ali?
It is at point E, not E, sorry.
طيب Hussein?
It will be between point A and D.
Here.
Yes.
This is the final point. Yes, this is the final point. This is the final point, steady state point. So the machine will oscillate around this. Of course, you can see here we have higher angle, and when we have this delta 0, we have a higher angle here. This is the steady state. Yes, so you can have, this is the, sorry, this shouldn't be, yes. The angle start here. If the fault occurs at this time, then the angle will oscillate, and then it will come back and forth, and it will settle down here. Slightly shifted up. The angle here is slightly higher than this. Okay, so this is the scenario. Of course, you can calculate the acceleration area. As we announced at last class, we have a quiz, very simple quiz. This will start after a few minutes. If you need a calculator to be ready with you or something like this, be ready. So it will appear after a few minutes. So the point will come down to here, and this is the acceleration. Of course, you can calculate the acceleration area, B mechanical multiplied by delta 1 minus delta 0 minus the integration over this curve, which is the BE during sine delta, and then this acceleration area post-fault power angle B max sine delta minus the this rectangular area. So you can have this is the acceleration and this is the deceleration area. And okay, again, if the fault is cleared here and this angle is known, after مثلا 70 degrees, the fault is cleared. So we can calculate the delta M, and we can be calculated. Assume that we need to know the critical clearing time or critical clearing angle. So what do you think? Delta max هتبقى معلومة ولا مجهولة? Known or unknown? If we are targeting the critical clearing angle or critical clearing time. Delta max will be known or unknown, similar to what we have done last example.
It's unknown.
It's unknown when? If we are targeting the critical clearing time. If we are targeting the critical clearing time, and we are utilizing the whole area of deceleration. So this angle becomes here, which is 180 minus this angle, and this angle can be calculated. So delta max is known, but the unknown is the clearing angle. And this is a critical clearing angle in this case. Is it clear or not? And when we say critical clearing, معناها ان we are utilizing the whole deceleration area available. And the critical point. In this case, delta max becomes known and the delta becomes unknown. Delta 1 becomes unknown. Where you clear the fault to utilize the whole area of the deceleration. So this is a critical clearing time angle. And this angle is corresponding to critical clearing time. So in this case, delta M is known, 180 minus this angle, and this angle is known, by the way, which is Bm over B max after the fault sine inverse. And you can get the critical clearing time. Similar to example number 3 and 4. So A1 or example number 1, 2. This is the A1 equal to A2. The critical clearing angle delta C, this is unknown, and we utilize all the deceleration area. So this is delta max is known. Delta max is 180 minus this angle, and this angle definitely is known. And the Bm is known equal to B max after the fault, which is this sine B max. Yeah, B max sine delta. Let us say this is delta prime, مثلا. This is delta prime. And the Bm is known, or B max after the fault is known, maximum value here is known. So you can get this angle. 180 minus this angle gives you the delta max. So delta max is known and delta C is unknown. So in this case, you can write A1 and A2. This is A1 and A2. Applying A1 equal to A2, you end up with this equation. You have Bm, Bmax, Bm is known, delta max is known, 0 is known, after is known. known, all things are known except delta C. You have here delta C, cosine delta C, and you have here cosine delta C also, maximum during, so you can have cosine delta C equal to this. This is a solution of this equation. All are known. Bm is known, all these are known, so you can get delta C, the critical clearing angle, can be calculated. But can you calculate the critical clearing time? Can you calculate similar to what we have done earlier? The quiz shown up or not?
It is shown, yeah.
طيب خلاص, let us stop for 5 minutes and then we'll come back. Okay. So let us continue. So for this, you calculate here delta CC, critical clearing time angle. Can you calculate now the critical clearing time? Can you calculate the critical clearing time? Can we calculate the critical clearing time by double integration of the swing equation?
We can find the critical angle.
This is the critical angle. This is the critical clearing angle here. Delta cosine delta C equal to this. So this is the critical clearing angle. Can we get the critical clearing time similar to what we have in that example? In that example, we calculate the critical clearing angle. And based on this delta C, we can double integrate the swing equation, and we can relate the critical clearing angle time with the critical clearing angle. So we can calculate the critical clearing time. Now my question is, in this case, can we double integrate the swing equation
But
or
here
not?
we will have the electrical term multiplied by sine delta.
Yes, and we cannot. We have here h over by f0 d square delta by dt square equal to b mechanical. Well, b electrical is not equal to 0, but equal to b max sine delta. And in this case, we cannot double integrate this. The TCC cannot be calculated on a closed form solution. Calculated on closed form. You have to integrate numerically this equation. You have to solve it numerically, and you can solve delta versus t. Assume that you are here, and then you have this solution comes from this solution of this swing curve. And in this case, you can see how much, where is the angle, delta CC. This is delta CC here. And you can see, and this is the time TCC corresponding to this value. So if you have the angle, you have to solve this numerically. The existing of this term make life is very, very complicated to get the critical clearing angle, critical clearing time. But this is the critical clearing angle. You have to solve the swing equation in order to get the critical clearing time. Do you have any question? I think there is no time for this example, but this is exhaustive example, and this is a comprehensive example. You are given numerical values system, and then we will discuss the critical clearing, the equal area criteria in all cases when we have step change in mechanical power, and how much the maximum, if we have fault here, if we have fault here, and all these, even if we have single line to ground fault, not necessarily three-phase fault, how to get the critical, the equal area criteria for system stability estimation or monitoring. Do you have any question? If you have any question, please continue with us. If you don't have, then you can leave.